Let's take a look at a special property about conservative forces. And in doing so, we'll invent a new concept that will be very helpful in our unit on energy. So imagine we have an object here at some initial position, and then it goes vertically up to some final position. I have a zero reference line down here where I'm stating y is equal to 0. Now, let's think about the amount of work done by gravity on this object as it rises up here. So think about it. How would you write down a formula that would allow you to compute the amount of work done by the force of gravity on this object as we go from this initial position up to this final position? See if you can get it. All right, well, here's the result. And gravity is what's called a conservative force. Only the initial and final vertical positions matter for calculating the work done by gravity. So we end up with asking the question, how much of the force of gravity is parallel to that vertical displacement? Well, all of it. Gravity points down and the displacement is up. And so we can see that we've got the work done by gravity then is mg delta y, and we have this minus sign out in front to conceptually get the signs right for if positive or negative work is being done. All right, pause the video and see if you can make that make sense to yourself. For example, when we raise this object and we go up, should we get positive or negative work done by the force of gravity? And then if we were to allow the object to fall down in the presence of a gravitational field, would gravity do positive or negative work on the object? Think about those questions and then come back and we'll take a look at the signs. All right, so we've got a little picture here where you can see gravity pulling down while we're going up, and those are in opposite directions. So the force of gravity in terms of direction would be negative, pointing down according to our coordinate system down there, but the displacement is positive, and so a negative times a positive would give us a negative amount of work. So would that work then in our formula? Let's do just a simple numerical example. So the work done by gravity is minus mg. I'll put the minus sign out. Let's just say we have 2 kilograms for our object. Gravitational field strength, 10 newtons per kilogram, and then we'll multiply it by some arbitrary initial and final positions. Why final? Why don't we use 8 meters and then an initial position of 2 meters, something like that. Cool, pretty easy. You get 6 times 10, which is 60, times 2, which is 120, so this would be minus 120 joules. And we would state then that the work done by gravity, if we were to go from a position of 2 meters to a position of 8 meters, up here, gravity would do negative 120 joules of work. And that should make sense because gravity is pulling down, but the object is being displaced up. Gravity is, in a sense, trying to reduce the kinetic energy of the object as the object is going up, right? Now we could throw the ball up initially and the ball would slow down as that gravity does negative work on the object, taking away some of the object's kinetic energy. Or we could push up on the object with an exact force balancing out of gravity, and the thing could move up at constant velocity, where the force of, say, our hand would be doing positive 100 joules of work on the ball, but gravity would be taking away 100 joules of work. And no change in kinetic energy as a result. Now, importantly, if we changed our sign convention, so we had negative this way and then positive that way, there's nothing wrong with doing that, then up here when we did the multiplication, we'd have a positive force of gravity and then a negative displacement, and it would still equal a negative amount of work in that case. All right, so it doesn't matter what sign convention you use when you do these problems at all. So what's the interesting special property that emerges with these conservative forces where it's only the initial and final positions that matter in the calculation of work? Well, let's go a little bit further with this equation and we'll write it out. The work done by gravity minus mg times the displacement. And let's just do some algebra. So you would get I'll leave the minus sign out in front and we'll distribute the mg inside. So you get mgy final minus mgy initial like this. And what we do arbitrarily, because it's useful to do so, is we call this something. We call this something. Pause the video and see if you can figure out what we call that. It's just a term. You might have heard of it before. But this very important calculation of multiplying the mass of the object times the gravitational field strength by its vertical position is a very useful thing to do. So think about it, what is it called, and then we'll see. All right, well, it's called gravitational potential energy. And the way you calculate it is simple. It's just the mass of the object times the field strength times the vertical position. So we can mathematically kind of clean up our equation over here. And this could be rewritten as a final amount of gravitational potential energy. And in fact, usually what I like to do is put a little g here for gravitational, put F for final, and then minus some initial amount of gravitational potential energy. And then we get that minus sign out over there, okay, to deal with. And the way we can consolidate everything now is if we wrap it up with the delta symbol, which is a change, we get minus the change in gravitational potential energy. Put a box around that. Both of these little formulas are important. The one right here, which is the general formula for how to calculate gravitational potential energy, and then this one right here. But the one here, relating the work done by gravity to the change in gravitational potential energy, is nice to use conceptually, as we'll see in just a little bit. Okay, now let's go through kind of a numerical example, but I want to point out a real special idea about how to interpret what gravitational potential energy really means. There's some things to watch out for that you'll see in a second. So first off, let's just do straight up simple calculation. So let's calculate using the math the initial gravitational potential energy. And so we have, let's just give this thing a mass here of 2 kilograms, like we said. So our formula is mgy, so 2 kilograms multiplied by 10 newtons per kilogram multiplied by 2 meters. And if we multiply that out, that is 2 times 10 times 2 is 40. Okay, so 40 joules. So the value of the potential, let me say that again, the value of the gravitational potential energy at this initial point is equal to 40 joules. Okay? Notice how I'm kind of saying that in a particular way. We'll see why later. Next, same calculation. Go ahead and do that one. Pause the video and calculate it. It's really easy to do. All right, you got it. It's just 2 times 10, which is 20, times 8, which is 160. So I won't show the calculation. I'll just write the answer there. All right, so now notice this. Let's speak this out. Let's talk about what has happened to the potential energy of gravity in this system as the ball has gone from 2 meters up to 8 meters. Okay, what has happened? Pause the video, write out a sentence that explains what has happened to the gravitational potential energy as the ball has gone from 2 meters up to 8 meters. Go ahead, give it a shot. So let's take a look. Notice the very specific language here. I'll elaborate in a second. The ball-Earth system has increased its gravitational potential energy by 120 joules. And here is the proof of that. The change in gravitational potential energy is the final minus the initial. We've already calculated it out numerically here. And when you do that, notice what we get. We get positive 120 joules. Now, what does that really mean? Does it mean that the ball has more energy? Well, this is a problem with language, really. And the way we speak about it in physics is it would be incorrect technically to say that the ball itself as a thing, as a physical thing, has now 120 joules of potential energy. That's not true. I mean, if you go look at the ball, it's not inside the ball. It's nothing to do with the ball itself. Instead, it's a little bit more sophisticated. It's the ball-Earth system. That's how we speak about where this energy now exists. To be more technical, it's stored up in what is called the gravitational field. And I've kind of drawn that over here. Here's like a picture of the Earth, not to scale, but try to draw it like in a curve just so you can see that, hey, we need to think about the whole planet right now. And you've got this little object going from here up, right, against the gravitational field. So that action of moving the ball and the Earth away from each other, separating these two massive objects, even though the Earth is a lot more massive than the ball, they both have mass. And separating these two massive objects, when we do that, we now have this gravitational field in existence between the two of them, and that stores up energy in that gravitational field. So I know that still probably doesn't help explain what's going on. This field is an abstract concept that we use to help us understand the world around us, but that's how we speak about it properly in physics, where we say that the system of the ball and the Earth, when they are separated now, they either store up energy in the gravitational field, or if they come closer together, they release energy from the gravitational field and turn it into different forms, such as kinetic energy. All right, cool. So very important point to make. All right, now let's make the connection between potential energy, or the change in potential energy of gravity, to the work done, which we've seen in that little formula. And we can see here that if we have a positive change, so there's been a gain in gravitational potential energy, that's occurred at the same time that there has been negative work done by the gravitational field. So as the ball goes up, the force of gravity does negative 120 joules of work on the ball. Okay, the force of gravity does negative 120 joules of work on the ball. But that energy gets stored up in the gravitational field of the ball-Earth system as gravitational potential energy, and here it is right here. Right, so we can get that energy back again, and if we let the ball fall, then there will be a decrease, so everything will just kind of become the opposite. There will be a decrease of 120 joules of gravitational potential energy, and then there will be a positive work done by gravity, and the ball will go down and will likely gain kinetic energy, assuming that there's no other forces involved or something like that. Okay, so there's this really important connection that exists here between the work done by gravity and the change in gravitational potential energy. That's key to realize. And of course, there's this little pesky minus sign you have to remember. And then the other thing that we're going to look at now through a numerical example is going to show the following statement. This is really important. Okay, the value. Let's write it out. The value of the potential energy, gravity, at one point alone is not enough info to tell you anything, meaningful. Okay, put a little box around that. Instead, what is important is the change in potential energy. We're always going to be concerned about 2 points. Okay, so you need 2 points, like specifically an initial and final, to reason with the concept of potential energy, as you'll see. Okay. And you can see that over here in the formula. It's the change in gravitational potential energy that allows us to know how much work is done by gravity. It's not the value at one point. So to kind of hammer this idea home, let's do an example of that you'll see right now numerically. Okay, here we go. So what I've done is I've changed the position of my zero reference line, as you can see. This is an arbitrary choice. You're always free to set y is equal to 0 anywhere you want. That won't change any of the physical nature of the system. It will change the particular numbers that you end up calculating, but everything will still work out physically the same way as it did before. So you can see here that there's still just 6 meters between the initial and final locations of this ball. It's just that this first location, the initial, is now 0 meters, and this is 6 meters up there. So let's go ahead and do some calculations. We'll calculate the initial gravitational potential energy. We'll calculate the final gravitational potential energy. We'll find the change in gravitational potential energy, and then we'll calculate the work done by gravity. Go ahead and give it a shot. Pause the video. Make sure you can do all of these exactly right. It's not really hard to do mathematically. but give it a shot and see if you got it. All right, so we're reminded of the general formula mgy. Sometimes you see mgh all the time. I typically like to use y as the just to remind you that it's a vertical position. But anyways, we got mgy, so we got 2 kilograms multiplied by 10 newtons per kilogram multiplied by 0 meters. Don't even really need to calculate it. It's 0 joules. And then here, this other one is 2 times 10 times 6. It's 120 joules. Okay, so you can see that the change would be 120 joules minus 0 joules, which would give us a change of positive 120 joules. Again, meaning that we have increased the gravitational potential energy of the ball Earth system by positive 120 joules. And likewise, the work done by gravity in that instance would be the negative of that, or negative 120 joules. We get exactly the same result, regardless of if we have set our y equals 0 on the ground level or moved it up to the next spot. Now, what if we set y is equal to 0 actually where the final position is? Go ahead and give that one a shot and see if you can calculate everything else out. And if you do it correctly, you'll show exactly the same thing for these two pieces of information down here at the bottom. The change in gravitational potential energy will still be positive 120 joules, and the work done by gravity must still be negative 120 joules. Give it a shot. And in doing so, you'll start to get the sense on how the actual number at one spot doesn't tell us anything. I mean, if you can just think about it for a second, the value of potential energy here used to be whatever it was, what was it, 40 joules here. The value here used to be 160 joules, but then when we translated y equals 0 up a little bit, it changed the numbers, and now we get 0 joules at this spot, and we get 120 joules here. Still a difference of 120 joules. That's the thing that really matters. Okay, so go ahead and give it a shot, prove it, and then we'll do it together. All right, so I have gone ahead and done it here. We can see that the initial value for the gravitational potential energy is up here, and it's negative 120 joules. Notice that its initial position is now negative 6 meters because it's 6 meters below our 0. If down is negative, then this would make this a negative 6 meters. So you have to include that up here. This is a vertical position is what y stands for. So there's my initial gravitational potential energy value, and notice how it's a negative number. Don't worry about that. It doesn't, remember, the value at one location is pretty much meaningless. It doesn't convey really any information. It's only relative to another value of potential energy that we can glean any information off of it. So we do that at the final spot, which is 0 joules, because y equals 0, and now we do the mathematical operation of subtraction. Final minus initial, so 0 minus a minus 120. Now the negative signs two negative signs turn into the positive, and we get positive 120 joules right there for the change in gravitational potential energy as we have gone from a position of negative 6 meters to a position of 0 meters. Still an increase in our vertical position of positive 6 meters. You can see that the work done by gravity also is the original value of negative 120 joules because of this conceptual rule that the work done by gravity is equal to the negative change in potential energy of gravity. We see this pattern over and over again with what are called conservative forces. Conservative forces will give rise to this relationship between the work done by those forces and potential energies that can be defined like we have seen here. So if you look at a simple setup like this, and I tell you, look, there's an object, some mass in space, there's a gravitational field pointing down, maybe this is on Earth somewhere, and I say, here's the value for the gravitational potential energy at this location, it's equal to 1,000 joules. Does that mean anything to you? And the answer to this question is no, it doesn't mean anything to me at all. This could be sitting atop a table in a room, depending on where you put y is equal to 0, which would be like way down here, y is equal to 0, dot, 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 right? Or this could be on top of like a massive building or something, I don't know. It could be anywhere, right? It's arbitrary where you decide to set y is equal to 0, so these values at individual points end up being arbitrary. The other thing to watch out for here is when you do calculate the gravitational potential energy of an object, like for example, let's do something kind of like this. Like let's say you're on an inclined plane or something, um, and you've got a ball right here, and you know that this has a height h to it right here. Okay, it's tempting to want to go potential energy of gravity at this point is equal to mg and then y, but we'll just use h for that, and say the ball has this amount of potential energy, mgh. The ball has that. That would be totally wrong to say that the ball has that, right? Instead, we want to say that the value of the gravitational potential energy at the location that the ball is at for the ball Earth system is such and such. And then we're good to go. All right. Um, Now you know that the ball has this ability to roll down. That's true. And then if we came down, maybe the ball moves down here or something to this location, like that. Maybe that's h over 2. We could calculate it again. The gravitational potential energy now at this point would be mg times its vertical position above the ground, and we're arbitrarily assuming y is equal to 0 there at the ground level, and you'd plug in h over 2 now, just if we parameterized everything in terms of h. Okay, so there would be half as much gravitational potential energy for the value at that location compared to how we started at the top, and then to find the change in gravitational potential energy, you of course would just subtract final minus initial. Okay, cool. Awesome. So this is just a quick introduction now to defining gravitational potential energy, finding its value at 2 points, setting our reference 0 line, and then also seeing how the change in gravitational potential energy is related to the work done by gravity with that little minus sign over there. All these things are going to kind of come together as we move forwards in energy and see how we can exchange energy from one type to another. Cool. All right. We'll see you in the next video.